Hey everyone, welcome back to the dining room shop, and welcome to part 2 of the Spindle Metrology series, where today we'll be talking about the concept of sensitive direction. This has got to be my favorite topic within the umbrella of Spindle Metrology, so much so that I've decided to dedicate this entire second part just to it and nothing else. So it'll be a little bit of a quicker one today. This is kind of the last little nugget of theory for now. And then in the next part we'll get into the practical stuff. It's like how we actually measure the air motion and process the data and all that stuff. But anyways, I hope after watching this you guys understand why I think this part is so cool. So let's get into it. So last time I was talking about the directions in which we can observe spindle air motion, and I brought up how we may not care about certain types of air motion depending on where the tool is. So let's get into that a little deeper. It's obvious that if we're turning an OD on a lathe, we probably don't mind a little axial air motion like this. And it's also obvious that if we're facing apart, we probably don't mind a little radial air motion. So we can formalize this by defining the term sensitive direction. For a given cutting process or metrology process, the sensitive direction is the one normal to the point of contact of the tool or the measuring device. So basically, for cutting tools, that's the direction which you would move in to increase or decrease the depth of cut. Or for measuring tools, it's just the direction in which that measuring tool can measure and is measuring displacement. Erroneous motion in that normal direction will negatively affect the results of whatever we're trying to do the most. Tangential motion at that point may not affect our results hardly at all, at least in the approximation where these movements are very small with respect to the part size. So, imagine the example of the OD on the lathe again. If the tool is on the side of the part here, air motion in this direction is very much going to affect the part size. That's the direction in which you would move if you wanted to affect the part size. However, if the motion's only up and down and the part's going tangentially to the point of contact of that tool, that diameter is not going to change very much at all, at least comparatively for a given displacement amplitude in both directions. This is an important point of note when it comes to radial air motion. Even though we call it one thing, radial, it's comprised of motion in two axes, x and y. So how our sensitive direction is oriented with respect to these axes is going to change the observed air motion that we see or that we actually care about. And I'll clarify here that for the sake of this discussion, we're just imagining a spindle with only radial synchronous air motion. Because we're talking about the shape of the part, we're leaving asynchronous out of the discussion for now. So our actual axis of rotation, the point at the center of the spindle, it's moving erroneously within the XY plane. And so we're looking at it, head on from Z, and it'd be moving, something like this, right? Pretty messy. But because it's synchronous air motion, these errors in X and Y, they're a repeatable function of theta, or where the spindle is within its rotation. So you can, this path can be plotted by plotting the air motion in X as a function of theta with the air motion in Y as a function of theta. But this is messy, and it doesn't really tell us much as a useful plot. So when our tool is fixed, like in the example of a lathe, it's fixed here. We call this fixed sensitive direction. The sensitive direction is this axis here, this x-axis, and I should label this for clarity. And this sensitive direction does not change. So if we measured the air motion by replacing this cutting tool with a measuring device, all we would observe is the error motion in the x-axis. So our observed error motion, we'll just call it E of theta in general, is equal to E sub x of theta. All we see is motion in x. But what if we're doing something else with our spindle, like boring a hole? So like using the spindle as the spindle on a jig bore or a boring mill. Now the tool is fixed to the spindle, and it's constantly rotating with it. And with it, our sensitive direction rotates as well. So here, the sensitive direction is in and out there, but as the spindle rotates and the tool is now in a new position, now our sensitive direction's here. And so, of course, it makes sense that we call this rotating sensitive direction. In the last video, when I used the Sharpie to trace out the error motion plot on that piece of paper, that was a rotating sensitive direction plot. Because as we move the Sharpie around, the direction in which we'll actually notice a deviation from the theoretical perfect circular trace is the direction radially, outwards, drawn from the center of the spindle to the Sharpie. So that changes as we rotate through a full revolution. And so for this case, depending on where we are within our revolution, we care about both the motion in x and y. And so we can write this one out and say our observed error motion for a rotating sensitive direction case is now going to be the error motion in x, which is a function of theta, cosine of theta, plus the error motion in y, which is a function of theta, times sine of theta. And so here we realize the fact, which I just find so cool. For a given spindle, the shape of a part turned by that spindle and the shape of a hole bored by that spindle are not the same. And in fact, let's take a look at these plots from my demo spindle. So this is that plot that I drew in the last video, the rotating sensitive direction plot. But here, we've got another plot, and this was produced by fixing the Sharpie to the table and then rotating the spindle and drawing on a piece of paper mounted to the spindle itself, so the Sharpie is acting as the lathe tool there. So that's a fixed sensitive direction. The Sharpie's not moving. And it's subtle, but it is still clear. These are not the same shape, no matter how I orient them. So this is what our lathe part would look like if we use the spindle to turn parts. But this is what our bored hole would look like if we use the spindle to bore a hole. Same spindle, same exact error motion, two completely different shapes. How cool is that? Maybe that's obvious and boring to some people, but I just found that absolutely fascinating when I first learned about it. And that's not all. Here's another clever point. So like I said, if we measure with our fixed sensitive direction here, where our tool lies on the x-axis, our error motion is of course just defined by the error motion in the x-axis. But if we rotate our spindle 90 degrees, or if you think about it in a different reference frame, rotate our tool, so now our lathe tool is down here, our sensitive direction falls on the y-axis, and our observed error motion, and hence the shape of our part, will be defined by the error motion in the y-axis. And so for any arbitrary orientation angle in between, and we'll call that angle phi, our observed error motion is going to be now defined as the error motion in x times cosine of phi plus the error motion in y times the sine of phi. And that phi is constant, that doesn't change, but depending on where your tool is or how you've clocked your stator with respect to the rest of the machine, that phi value will change, and hence your error motion, your observed error motion will change. Let's go into Matlab and take a look at a little demonstrator that helps us visualize this a little better. So we're here in Matlab where I've modeled the error motion of a sample spindle. So it was done by just sort of making an arbitrary Fourier series with some various frequencies and amplitudes to approximately represent a real spindle's error motion. What we see in the middle plot here is the actual motion of the spindle axis in the xy plane as it rotates, that sort of squiggly figure I drew out before. On the right, I've got a plot of the rotating sensitive direction error motion that results from that movement of the axis of rotation. On the left, I've got a fixed sensitive direction error motion plot, but what we're able to do here is actually change the value of phi with this slider, so I can basically view the error motion from any angle around the spindle. Basically move my indicator or move my lathe tool to a different angular position around the outside of the spindle. And it's neat to see how the shape of our part, or our observed error motion, changes a lot actually, depending on what angle we're coming at it from. So in this example here, if we turned a part with the lathe tool sort of at 0 degrees or on the x-axis, we'd have a part that's mostly 3-lobed. But if we moved the tool to the top of the part at 90 degrees, or rotated the spindle stator 90 degrees with respect to the rest of the machine, now our part is 4-lobed instead of 3-lobed. Same spindle, same error motion, but we can produce either 3-lobed or 4-lobed parts depending on where the tool is with respect to the spindle. And then if you look here on the right, if you bored a hole with the same spindle, you get a different shape entirely, something completely separate. And you can see as I move the phi slider here, there's no value of phi that produces the shape of the rotating sensitive direction plot. There's values that look close, but it's still obvious that that is a completely independent and unique shape. How cool is that? You'll also notice I've got the total synchronous error motion here displayed at the bottom of the plot. This is just the value of the peak to valley amplitude of our error motion here, or practically, how round our final part will come out, the total roundness. And you'll notice that, that too changes as we change phi, as the x and y error motions may sort of constructively or destructively interfere depending on the angle that we're viewing them at. So a wise man named Bob Greta once said, hey, what if we plotted that value for the peak to valley error motion as a function of phi, and then we could see at what orientation angle the error motion is at a minimum. And so that's what we see here. For this example spindle, if you were really out for blood and chasing down every last nanometer on your diamond turning lathe, you can look at this and now know, okay, I want to mount my spindle stator at 170 degrees with respect to the rest of the machine, as at that angle my part will be the most round possible, rounder than if I mounted my spindle at any other angle in any other way. And so this is what we call Greta optimization. Practically, it's a pretty niche technique, and it's really up to chance and your particular spindle how much of a gain you can get from it. So sometimes you might find an obvious and significant global minimum, but other times the error motion might be fairly consistent over the whole range of phi, and you don't get that much of an advantage. But again, I mean, this is for people who pull a brand new professional instruments air bearing spindle out of the box with, sub-micro inch error motion no matter which way you look at it, and say, how can we optimize this even further? So, pretty niche. What's cool is that, for all of this stuff, all you need to measure is the fixed sensitive direction error motion in two directions, x and y, or at 0 and 90 degrees. And from that you can calculate the rotating sensitive direction and the fixed sensitive direction from any arbitrary orientation angle. So basically, just to be clear, I don't have to take 360 individual error motion measurements at every value of phi to do Greta optimization. I just need two measurements, and they can be done simultaneously, and then I can mathematically determine everything else that I could ever want to know. And so that's sensitive direction for you. It's an idea that's perhaps not completely obvious, but it's important to know so that you can measure your spindle accordingly and know what you care about. And really, it's just a neat concept in general. I like it a lot. Next time we'll actually go over how to measure all this stuff and all the practical elements associated with that. So stick around. Hope you guys enjoyed. As always, drop any questions in the comments below. And thanks for watching.